Okay, welcome back. So we worked with quantifiers, the universal and the existential, and then we worked with, I guess, the universal conditional, the existential, and that sort of stuff. Oops, let me get my microphone over here. Today we're going to combine the existential and the universal quantifiers together. Okay? So these are statements with multiple quantifiers, which do happen. Okay. If you're taking calculus, you are familiar with the sort of universal existential. For all epsilon greater than 0, there exists a delta such that for all x within some distance of c, if L minus f of x, that thing, okay? And we torture students every year in Calc 1 with that. That is an example of the universal existential. Okay, okay, so that's where we're going to start. And the form for all x in some domain D, there exists a y such that x and y satisfy some predicate p of xy. Okay, so first about proving these things. The first type is proving the thing is true. For the finite case, when you only have a finite domain to deal with, you can just do the method of exhaustion. And the book uses tables. Okay, so I just indicate this as a table, and we'll look at problem number 9 in the book. So number 9, D is equal to E. So maybe in this statement I should say there exists a Y in some other domain E. Okay? So in this case, both this D and this E for the X's and Y's are the same. So D equals E, and it's a finite list of numbers, -2, -1, 0, 1, 2. Okay. Okay, so the statement in part A, for all x in D, there exists a y in E such that x plus y is equal to 0. Okay, so we make a table. I have to find a corresponding y for every one of these x's, and it doesn't have to be like a unique y. All right, this just says for all x out there, there exists some y, I don't know which one, such that x plus y is 0. So I'm going to find a corresponding y for each x and show that x plus y is in fact equal to 0. Okay? So there's -2, there's -1, there's 0, 1, 2. So you find the corresponding y value, -2 and 2, the additive opposite, -1 and 1, 0 and 0, 1 and -1, 2 and -2. Okay, and in each case, those will add to 0. And so this is true by method of exhaustion. Okay. In your homework, or at least when I did the homework, I generally didn't even bother with a table. I just kind of go through mentally. But if you're doing that, you're leaving yourself open to committing errors, and you'll make little mistakes, and you're going to lose points in the homework. And if I make a test in WebAssign, you'll make mistakes there too. So a table is a surefire way. It's good evidence if somebody asks you for it. Here it is. Okay. The harder type problem is when you have to do this in general, okay, which is what you would have had to do with the calculus. For all epsilon greater than 0, there exists a delta greater than 0 such that if x minus c is less than epsilon, then f of x minus L, sorry, if x minus c is less than delta but greater than 0, then f of x minus L is less than epsilon, that thing. If you remember, doing those proofs was kind of difficult, and you have to do a lot of back engineering. But in general, what the process is that you're solving for y in terms of x. And then you show that this y satisfies the given predicate. Okay, so in calculus it was a lot harder because it's actually there's also there's like 3 quantifiers in there, at least in my opinion. There's 3 quantifiers, so a little more complicated. And on top of that, it's absolute values. Okay, so if you're dealing with something that's just an equation, it's a lot easier. So let me show you the equation version. And you know, if you're not taking calculus, this will be a good warm up for when you get there. So for all x in the integers, there exists a y in the integers such that x equals y plus 1. Okay, so this is actually number 41, part B. If you're following along with your book, they want you to show that this is true. Okay? And in calculus, sometimes even if you get a teacher who's into this kind of thing, they'll set it up as kind of like a back and forth between 2 people. So you have to imagine, especially for me, I have maybe a student comes into my office here, and I'm sitting at my desk or whatever, and the student, you know, he doesn't believe this is true, right? He doesn't believe that for every x there exists a y such that x equals y plus 1. Okay? So he walks into my office, or she walks into my office and says, hey, what about x equals 3? Okay, so I think in my brain, okay, if x is equal to 3, then I have to solve for y, basically, right? So y is equal to 3 minus 1, which is 2. And then I say, okay, yeah, what about it? Well, y equals 2. That will work. Okay, then the next day, he's like, oh, what about x equals negative 1, right? Maybe a negative number won't work. It's still an integer, but maybe it won't work, right? So I sit there for a second and I think, okay, all I got to do is set up this equation, right? Negative 1 equals y plus 1, and then y equals negative 1 plus negative 1 is negative 2. So here you go, kid, y equals negative 2. Okay. All right, then by the third day, I'm getting a little peeved, right? I got a lot of stuff to grade. I got all kinds of weird curriculum updates to do, just grade disputes all over the place. So I need to find a different way to deal with this kid, right? He's not getting the message. And again, he comes in and he says, well, what about x is 10, right? Maybe double digit numbers don't work the same as single digit numbers. So what I do, I know a little bit about computer programming. So what I do is build this little machine. And I don't know much. I grew up in the 80s, so I remember tapes and stuff like that. In the beginning of computers, they actually had cassette tapes that you would store your computer programs on. Before then, they had reel-to-reels. But anyways, I set up my computer. You know, it's programmed, so the thinking is done now with the program. And basically, it takes an input of x, whatever x is, and then it solves this equation for y. So y will equal 9. And in doing so, I never have to deal with this kid again, right? And then the computer just says y is 9, and it turns out the student was just messing with me, right? He doesn't have anything better to do. We didn't give him enough homework, so he's in here in my office screwing around with my brain. He goes away, and life can continue. I can go back to my work, right? Okay, so that's kind of what we want for these types of proofs. We want to back engineer or program this formula such that if anybody walks into the office, I could just give them I can give him the computer, he'll input his value, and output will be this thing. Okay, and that constitutes a legitimate proof in this case. Okay, so writing that up is an art in all of its own, all to its own. She doesn't give you a lot of direction at this point in doing that sort of maneuver. I'll just give you sort of a flavor for how that happens. I think chapter 4, we'll look into that more, working with proofs and setting them up stuff. Okay, so what I would do here is just say, suppose y is equal to x minus 1. So I've kind of gone through the mechanics here and back engineered this formula, right? So whenever the student walks in, it gives me an x value. All I have to do is take this equation, x equals y plus 1, and solve it for y. So I'd get y equals x minus 1. So that's what my machine basically is. Suppose y equals x minus 1. One prerequisite I have to make sure is that this y value is actually an integer here. So, the difference of two integers is always an integer, and we'll talk more about that kind of stuff later. It's called closed. The integers are closed with respect to subtraction. So anyways, thus y will be an integer. And then we note y plus 1. We want to show that this equals x, right? So y plus 1, if I do a substitution in for y, I'll get x minus 1 plus 1. And then that will give me the x that I was after, okay? Thus, for any x that you give me, I can find a y. In particular, the y is x minus 1, which is in the integers, such that x equals y plus 1. Maybe I would write that out later on. So I'm going to leave it at that, and we'll work more on proofs in the next chapter. Okay, so that's the general case, which is always challenging to the Calc 1 students, but it is just a special kind of proof, the universal existential. Now let's take a look at proving something is not true. This is a lot easier. And we'll look at 41 part B, or sorry, 41 part A. So 41 part A, there for all x in the positive integers, there exists a y in the positive integers, so I need a little positive sign there. There exists a y in the positive integers such that x equals y plus 1. Okay, so basically we kind of have to go with the counterexample type deal for all x in z. So let's consider some particular x, right? So consider the number 1, which is obviously a number in the positive integers, right? In particular, then, if y, so consider this equation when you plug 1 in for x. Okay, so note letting x equal 1, we have 1 equals y plus 1, which implies that y is equal to 0. Okay. Okay, this is automatically a problem because 0 is not in the positive integers. The positive integers only the count 1, 2, 3, the natural numbers. Okay, so hence, at least in this case, there exists an x in the positive integers such that there is no y in the positive integers where x equals y plus 1. Okay, so we found basically our counterexample. Okay, thus the statement is false. Okay, so that kind of proves a lot easier. Obviously, in the homework, you won't have to write out anything. They give you choices or just A, B, C, or D, and they do the work. But if you keep on taking math, they're obviously going to expect you to write out these proofs yourself. Anyways, section 2 then, if we had the universal existential, now we have the existential universal. Okay. And in particular, the form, there exist in X and D such that for all Y and E, X and Y satisfy this predicate. Okay. I'm not sure if the software WebAssign uses this line here. They may use commas on both of them. I'm not sure, so I apologize if that's the case. Anyways, again, proving true is easier for finite cases because you could just do it by method of exhaustion. And in particular, let's look at number 9. So number 9, again, we have D equals E equals -2, -1, 0, 1, and 2. Okay. And then part B, they want us to prove that there exists an X in D such that for all Y in E, X plus Y equals Y. Okay, so again, we could do this table thing. Usually when I'm doing the homework, honestly, I'll just do it in my head. But like I said before, you want to be careful so you don't lose points on tests. So table is a good way to go. So anyways, this time I'm looking for an X, a corresponding X for every Y in this set such that X plus Y equals Y. So the values for Y, -2, -1, 0, 1, 2. And then I'm looking for a number such that when I add it to this number, I get out the same number. So it's the additive identity we're after, and that's the number 0. Okay, so 0 will work in every case, and you can check that. And there it is. That's kind of like a proof, right? Okay, so hence the statement is true in this case. And let's move on to the general version. Okay, so in general, again, now we're dealing with, so I guess the big difference is instead of finite, you have an infinite number of cases, and that was true before there. Proving finite cases, you just do a table. But proving infinite cases is a little more complicated. Fortunately for this version, I just look and do it by inspection. Quote unquote, teachers will say that sometimes. I did it by inspection. I just looked, right? And that just depends on your familiarity with numbers and the basics. So the general version, anyways, let's take a look at number 16. And here we're trying to prove there exists a number u and the real numbers such that for all v and the real numbers, u times v equals v. Okay, so does there exist a number such that for every number, when I multiply it by it, I get that second number back out? Okay. And yeah, obviously u has to be equal to 1, and that'll work. So if I wrote that up, I would say something like note u equals 1, and you have to note that that thing is in the real numbers. And then let v be a particular but arbitrarily chosen element of R. I just usually say payback. So you talk in generalities, and it's like killing an infinite number of birds with one stone. Okay, so let v be a particular but arbitrarily chosen element of R. We note then u times v equals 1 times v, which will equal v. And so because v was chosen to be arbitrary, it holds true for all values of v. Okay, so I would just say this, thus the statement is true. Right? All right, so that, by inspection, generally in the homework, that's what you'll be doing. You'll just say, okay, it's true, and here's the element. Okay, and again, it's like it's choices, it's multiple choice problems. You're not going to have to write out the proofs yet. Chapter 4 will focus more on writing out proofs. Anyways, proving false. So you'll just want to show that it's not, it's kind of like do a counterexample type proof. So let's look at, so I'll just use counterexamples. Okay, so let's say at 41, part C. And here we're trying to prove there exists an X in the real numbers such that for all Y in the real numbers, X equals Y plus 1. Okay, so what we're going to do is kind of pick a random Y value and show that there doesn't exist a particular X that will work. Okay, so well, consider then Y equals 1 and Y equals 2. Okay, so for Y equals 1, what do we have? We have X equals 1 plus 1, which equals 2. Okay, then for Y equals 2, X would need to be equal to 2 plus 1, which equals 3. Right? So just for these two elements, there's no particular X, one individual X which works. Right? So there's no one X such that for all real numbers, X equals Y plus 1. Now this isn't about uniqueness. You can have more than, it's not that there's other ways to write there exists a unique X, and what they do is kind of usually put like an exclamation point in here, or maybe they put it in front. It's not about uniqueness. Here we couldn't even find one that worked for all Y. Okay? If you could find more than one that worked for all values of Y, then you would really be set. Right? What this is showing is that it doesn't even work for one particular, or for two particular picked values of Y. We can't find one that works here. If I could find more than one, that would be fine. But so there's one issue that we'll talk about more. What I'm getting at is, okay, so sometimes I kind of babble on, but what I'm getting at is it's kind of a little bit ambiguous when you're first starting to work with these quantifiers. And you need to iron that out, and hopefully you'll do that in the homework. Okay, so there's subtle issues about uniqueness, and then on top of that, there's also issues when you interchange these. It sometimes changes the truth value, sometimes it doesn't. Okay, so you're going to get a lot of practice with that. Okay, so anyways, let's just move on to negations. Right. So we want to be able to negate one of these guys, so we'll go to kind of our symbolic notation, the negation of a universal existential. So for all X in D, there exists a Y in E such that P of X, Y is true. Right. So to negate this, what you're going to do is just go through these guys and flip their quantifiers, and then negate this thing, whatever it is. And sometimes this thing is an if-then, sometimes it's an and. You'll have to use De Morgan's or other equivalent laws. So let's do it. So this will end up being there exists an X in D such that for all Y in E, it is not the case that P of X, Y is true. Sorry, I went off the page there. Okay, so negating that, you just flip the quantifiers and negate the predicate. Okay, so the other case, existential universal. There exists an X in D such that for all Y and E, P of XY is true. So to negate it, you just flip the quantifiers for all X and D. There exists a Y and E such that P of XY is not true, okay? Or not P of XY. Okay. Right. So let's take a look at some of these, and you're going to be doing formal translations, going from informal talk to formal logic, and so on. Let's look at number 13. Okay. So for all colors C, there exists an animal A such that A is color C. Okay, so one thing that'll help a little bit is just being able to translate this into your informal speak. Hopefully you translate it right. So anyways, for all colors, there's an animal A such that A is, okay, so for every color, there is a corresponding animal, okay? Or there's an animal of every color. So just informally. Part B, they want you to negate it and then rewrite it informally. So there exists a color C such that for all animals A is color C. Okay, so informally, what does that mean? That means that there's a color out there. There exists a color C such that for all animals, there's a color. Oh, sorry, I forgot to negate this part. There's the issue. Such that A is not color C. So there's some color out there that such that there's no animal that that has that color. Okay, so informally, maybe we say there is a color that has no corresponding animal. And again, this is not uniqueness. There could be more than one color out there with no corresponding animal. Okay. But these next ones are kind of neat or kind of sad in a weird sort of way. So they're phrases that we hear in English, and it's like you can immediately translate them into logic speak with varying results, right? So everybody loves somebody. It's like maybe a Valentine's Day card or something like that, right? So let's take it apart and destroy it using logic. So first I'm going to translate it formally. So for every P, and so we need two different people, right? So every P1, P sub 1 in the set of all people, there exists a person P2 in the set of all people such that this P1 loves P2. Okay, so that's everybody loves somebody in logic speak. Now they want us to negate it and then reinterpret it. Okay, so there exists a person P1 in the set of all people such that for all persons P2 in the set of all people, P1 does not love P2. Okay, so there exists at least one person that pretty much doesn't like anybody. All right, so there is someone who doesn't love anyone. It's kind of funny. This is a good Valentine's Day card. This, not so much, right? Let's try another one. 36. Somebody trusts everybody. So again, it's the same kind of problem. Part A, for all. No, there exists a person P1 and the set of all people, such that for all P2, all persons P2 and the set of all people, P1 trusts P2. And then we want to negate it. So for all P1 in the set of all people, there exists P2 in the set of all people such that P1 does not trust P2. Okay. So what does that mean informally? There's somebody that nobody trusts, right? Or rather, it's for all P1, there exists some person. So it doesn't have to be one particular person. Every one of these guys could distrust some different person, right? Okay, so for everybody has somebody they do not trust. That's probably better. Everybody has someone they don't trust. Okay, so now let's get into the idea of changing the order of the quantifiers. It doesn't automatically sort of change the truth value. If you change the order, it could still be true. So if your original statement is true and you change the order, it could still be true. Right? It's that sort of thing, but it could also be false. So we want to analyze that on section 4, changing the order from universal existential into existential universal, or vice versa. And just note, it may change the meaning. You cannot go off doing this willy-nilly and expect things to be hunky-dory. Okay, we'll go with the Tarski diagram here. Rather than me reproducing it, let me go to the book and just borrow it. Cheap, loose leaf book. Oh, it's already open to that page. Almost. All right, so there's my Tarski diagram. Okay, so let's see what the question is. This is example 3.3.8. It's actually on the bottom of page 137. Let me get that page. It's shown twice in the book. But... Okay, so part A, what they want you to do is kind of compare and contrast, I guess. So part A says for all squares y, there exists a triangle X such that X and Y have different colors. Okay, they want you first to figure out if that's true or false. So let's take a look at the diagram. Of course, it's not all going to fit. So for all squares y, there exists some triangle out there, x, such that x and y have different colors. Okay, so it doesn't have to be, one particular triangle. For every square, there could be a different particular triangle that doesn't work, right? And we're considering colors. So on this diagram, there's blue guys, there's gray, and then these guys are black. Okay. Okay, so we're comparing squares and triangles. For every square, we have to find a triangle that has different colors. So I'll start with this square E, and this triangle has a different color. Okay. Then this square G, this triangle has a different color. This square H, this triangle has a different color, and then this square J, the triangle right next to it has a different color. So it's true by method of exhaustion. Okay, part B, I believe all they do is interchange the quantifiers. Right? Or this is like statement 1, and then they have statement 2. It's not part B. So part B, there exists a triangle X such that for all squares Y, X and Y have the same color. Sorry, just one second. It seems like what's annoying me is it seems like in the homework sometimes they'll literally just replace this and this with each other. Okay, they'll just rotate the existential here and put the universal letter here. Okay, and keep squares here and keep triangles here. In the book, the way they're kind of introducing it, it's kind of they want you to take this whole statement with its domain and pull it over to here, and then this whole statement. So just be aware that there may be an issue between the book and WebAssign there. WebAssign's pretty solid. Don't let me, but just be careful is all I'm saying. Okay. So anyways, we want to see if this guy is true, and what I'm saying is that changing the order doesn't normally or have to, it's not like a negation, right? So I didn't exactly negate the statement. That's kind of what I'm getting at here. I didn't negate. So if you do negate, it's kind of like you will flip the quantifiers, okay? And then this last statement will be negated. When you're changing the order, it's not the same thing, right? At least in this context with what the book is talking about, moving this quantifier with its domain over to here and move this quantifier with its domain over to here, that is definitely not a negation. So anyways, without further ado, let's just see what the truth value of this guy is. So for every triangle X, there exists a triangle X such that for all squares Y, X and Y have the same color. Okay, so I have to find a triangle such that for all squares, X and Y have the same color. But that's not going to be possible because the squares have different colors. So there's no triangle that has more than one color somehow, So that's patently false. Just be aware that that's not going to always be the case. Interchanging the quantifiers sometimes will not change the truth value. Okay, let me beat that to death. Let's get into more formal logic notation. I think this stuff is the bee's knees because it could quickly be programmed into a computer. and let the computers kind of figure it out, you know. So 5, formal logic notation. So first off, we're going to be using the universal conditional and the existential and in these problems. Okay. And they're going to be using a lot of parentheses. All right. So statement such that for all x and d, p of x is true will look like this for all x with x and d implies p of x. Right? And then the existential as a and statement. This is there exists in x such that x is in d and this other predicate holds. Okay, so I think we've done that before. This is a little bit more formal logic notation with the parentheses. Okay, we want to do this now also with multiple quantifiers. And what's going to kind of change is this part right here. Okay, we're going to put the other quantifier in that position, or in this case, the other quantifier will go in this position. Okay, so let's look at some examples of doing that. This is 46, and these are all Tarski type problems. There is a triangle x such that for all squares y, x is above y. And for the predicate, they're going to have little functions. So the function for x is above y is going to be is above x comma y. And then the function for it being a triangle will look like this, triangle of x, and the function for being a square. They're pretty self-explanatory, right? But they are listed in the book if you are having your mind blown right now, like what the heck is he doing? They are all in the book. Okay. Okay. Right. So let's go ahead and translate this into the formal. So there is a triangle, there exists. That will be the existential and. So we'll start with there is an x, basically such that, and then we put x as a triangle. So I use my triangle function here. Triangle of x. And then I'm going to put in my other universal, the universal part, right? So, and I'm going to put a parentheses there to contain it all. For all squares y, so for all y, such that y is a square, so we'll say square, use the square function, and we're using the universal conditional. So for all square y, that implies x is above y, and we use the function notation. Okay, and then the hard part is figuring out how many parentheses I need. You could just count the forward facing, 1, 2, 3, and then plop them in. Okay. So a lot of parentheses. The book will give you multiple choice, or sorry, the web design will give you multiple choice for these. It's kind of hard to see, it barely fits in the screen. There it is. Okay, then we have to figure out if this thing is true. So again, let me find the picture of this character. Where are you? I'm not seeing you. This Tarski guy. Oh, it's in the exercises. we need to figure out if that's true or false. So here's our Tarski diagram again. So what was it asking? There exists a triangle such that for all squares, the triangle is above the squares. Right? Yeah, this triangle will work for all squares, right? So that is true. There could be more than one. I don't know, but I found one, so I'm done. So it's true. And maybe the software will ask you for which particular triangle works. True, triangle A works. Okay, so you always want evidence and proof. It's a good idea. This triangle A is right here. Okay. Then they want you to negate the thing. Okay, it seems like a tall order, but it's no big deal. You're just going to flip this, and then you'll have to, because this is an and statement, you'll have to do De Morgan's here. So this would be not triangle or, and then you have to negate this thing. So that will flip this into an existential, and then we have to remember how to negate an implication. So let's remember how to negate an implication. So how did that work? Either you get, if you don't get the work on time, then you're fired, right? And then we want to negate this. So either you get to work on time or you're fired. That's equivalent to saying if you don't get the work on time, then you're fired. Either you get to work on time or you're fired. Then we need to negate that and use De Morgan's. Okay, so that would be P and not Q. Okay, so that's how we negate an implication. So now we go back to this big long thingamajig and first flip the quantifier for all x, and then parentheses, negate the triangle function there. And then change this to an or. And then we want to negate this universal, so this will become existential. And then this part we use these equivalent forms to rewrite it as an and. Right, so we'll have square y still, and not above. And then we need our parentheses. I think there were 3 of them. And then we should be good to go. Okay, let's try one more, and then that'll be it for this section. The next section is pretty quick. Anyways, here's 48. For all circles x, there exists a square y such that y is to the right of x. Okay, so first they want you to determine if it's true or false. So again, we can go to our picture. For all circles, there's a square that's to the right of it. So it doesn't have to be the same square, but for all circles, you need to match it up with a square, okay, such that the square is to the right of the circle. So for all circles, I need to find a particular square. Well, hey, this isn't going to work here, down here. There's no circle to the right. Sorry, there's no, for that particular circle, there's no square to the right of it. Okay, so this is patently false. Then we need to rewrite it formally and then find the negation. The negation is going to be true. If I did not make that clear in the last problem, once we figured out whether this was true or false, its negation is automatically, in this case, will be false. Okay? So that's why I didn't bother going through that. Okay, so anyways, formally translate for all, then we use our function notation for all circles. Well, no, that's not how we say for all objects x, and then we use conditional. If object x is a circle, then and then we put our existential here, then, and we're going to put it in parentheses to mark off where it is, there exists some object y such that, and then we put a conjunction, y is a square, and y is to the right of x. So the function is right. And then we need 3 parentheses. Okay, so that's part B. Part C, we need to negate the critter. Okay. So part C, then turn the universal into existential. There exists an object x such that, and then we have to change this part into an and statement. So you keep circle of x the same, change this into an and then we have to negate this thing. So that will become a universal for all objects y. And then this will become, you do De Morgan's on it. So this will be, there's not a square y, or it's not to the right. Okay. And that's pretty much the spiel. There's not like a lot of these kinds of questions on there, but I think they're really cool because I just love getting rid of English. I think English is so, there's so many ways to interpret things. I think on the internet with people yelling at each other, you know, if everything was logic and there would be nothing to yell about, maybe that would be the problem. Everybody wants to fight with everybody else. Oh, in a perfect world, right? Okay, so thanks for listening. We'll see you next time.